running. Here's the bootloader, boot menu. So I finally have a good way to print stuff to terminal, and you might have noticed that I've also used some like fancy colors, including for the background. I basically asked ChatGPT to give me a bouquet night theme because that's the color scheme I use for the new Vim config. But that's besides the point. So in this video, I just wanna step through the code and look at just review what I have implemented, because I've like made some few commits after the last video. So the first thing we do is we initialize I'm currently at the kernel main entry point, right? And the first thing we do is initialize the terminal. And so this one is the foreground and the background, right? And I guess black isn't really black in here, but yeah, white is also like kind of different. But so this is the foreground, which is the default color of the text. And let's see what init does. Okay, so we take two colors, right? And the first thing is we initialize the frame buffer, and you notice that I'm kind of using global variables in here. I mean, I ran into a kind of an edge case where I wanted to do something like this. So basically take a format string argument and like any number of arguments, right? Basically printf in Zig, let's say. And what I wanted to do is I wanted to create a writer from that and just pass it to format because it takes a writer. And I couldn't do that with if I had used something like, so let's say const terminal equals struct, and basically just encapsulated everything inside this struct. This I couldn't achieve this because then all of these functions, so things like right char and stuff would need to have a mutable pointer to the terminal type, right? But the writer interface itself, I obviously needed to write a writer interface to get this to work, but the writer interface only allows non-mutable self-type. So in my write implementations, I couldn't like call these functions without using global variables. Well, maybe there is a workaround, but right now that's just the way I went with it, and I looked at some other implementations, like similar kernels in Zig, and they kind of were just using global variables as well. So yeah. But anyway, so first thing we do is we initialize the frame buffer, and I'll go a little bit into that later. And of course, frame buffer is an initialized variable in the beginning, and then we fill all of it with the given background color, so that we color our screen with the given background color. And another thing is, so after we initialize the frame buffer itself will contain a font, and that's another thing I'll get into later. Pixel width is pretty much self-explanatory, and the reason this exists, so is the number of actual bytes in each row, and this can be more than width into pixel width, so it can be more because of padding or alignment between these rows. So basically, if I had to draw a diagram, so if this was our frame buffer and this was row 0, and it is obviously composed of pixels, and the row is composed of pixels, so imagine these are the individual pixels, and we have the second one, right? And now what this basically is, the point of this is trying to say is, when we get to this second row, we could be skipping some extra bytes before we get to the second row, and that those bytes might exist because of some alignment or padding issues, right? Or alignment issues or padding, rather. To me, visibly, a row is, it starts from here up until here, and then it starts from here, right? But in reality, that row could be like spanning across a few more bytes before I see the next series of visible pixels, right? So that's basically why bits exists. And obviously I use it when I'm trying to like calculate the actual length of the buffer. So to calculate the length, what I basically do is I use the bits, which tells me how many bytes, actual bytes are in each row, and then and the height, I mean height isn't affected by padding, so I multiply that with height, and this gives me the number of actual total bytes that are in the allocated buffer. But since we're doing an abstraction using pixel, I basically divide that by with the size of each pixel, and that's how. So when doing pointer cast, I cast it as a many item pointer. So I first cast it as a many item pointer to pixel, an area of pixel, and then I do some slicing so that it is converted into a slice, so that we know the length of the buffer. And that's basically the initialization part. Of course, we return a null if I don't get a frame buffer from lim itself, but I think that won't often happen. And a few things. So color. So color is encoded as a RGB value in hex, right? And I have used some amount of colors, and there are also like semantics around its colors. So I use red if I'm like trying to do alert or error and similarly. Yeah. And since this is an enum, I defined a 2 pixel functions that converts it into an int. So the core of text rendering it involves mapping each character. So if I have a character char, char character, then I need to find its bitmap representation in the font that we are using. So in this case, I'm using Terminus font as I discussed before, and we find the bitmap representation of that font. So if you get bitmap for that character, and then we iterate over the pixels in the glyph bitmap. So glyph bitmap would be this, and it's a little bit complicated because each pixel is going to be a single bit. So we have to do some a little bit of bitwise operations to get the actual pixel, and then once we find the pixel value in the bitmap, we basically color that. We basically set the corresponding frame buffer pixel according to how the bitmap was given. So if I look at this code, we iterate from font header to height. So in this case, height will be 16. So this might as well just be so 0 up to 16. So we have to do it 16 times because there are like 16 rows in that font in each glyph, and then each glyph will be a byte. I mean each row will be a byte, and then we actually need to go beyond the byte and look at the bits. So we since its byte will be 8 bits, we do it 8 times, and then we to get the actual bit, we do some bitwise operation, and then if the bitmap that we got into mask is not 0, that is if it is 1, then we use the foreground, and then we color the corresponding pixel accordingly. Otherwise we just use the background. So how do we access a particular pixel in the frame buffer? It is done by the get offset, and I mean it's much simpler in this case because that's kind of one of the reasons I did the pixel abstraction, because in this case, since it is a linear buffer, I multiply y with how many bytes are in, how many pixels are in each row, and then we just add x. So that will give us the offset in the buffer according to the x and y coordinates. But if I was not using that abstraction, I would have to use basically what the step article points out. So this would be the starting address of the buffer, and then we multiply y with bits, and then x with the pixel width. Yeah, and I think it's easier that this way. So if we have a pixel, then I can just write the color that we are given to the corresponding offset, and that way we will see the color being written in the screen. And we obviously have to account for x and y positions to handle line wrapping and spacing. That's something like scrolling. It was much easier to expose this through frame buffer, because we can optimize some things if we have direct access to the frame buffer but I could have just done this through the terminal abstraction itself, but it's much faster this way. So how do we implement scrolling? So this is the end of screen, and this is how many pixels are in each line. We reinterpret the buffer as U62, so we are looking at 2 pixels at a time. And then so the basic idea is, basically we are at the last row. So to simulate the effect of scrolling, what we need to do is we need to copy whatever is in this last row to the row above it, and similarly we copy row 1, everything in row 1 to row 0, and essentially row 0 will be will let out, and then we will have the last row remaining, and it will be empty. So now we can basically write to the last row. And the way we implement this is, I think it's not that difficult, but I kind of found or stumbled across a little small optimization. That way we can since we're only just copying stuff and overwriting values, I can do it 2 pixels at a time. So let me just read through the comments. Maybe it will explain. Maybe it will be a little bit more clear. So we're copying 2 pixels at a time. We're going to divide the number of pixels by 2. So how many pixels there are? By 2. And we're not copying the first row. So we subtract the number of pixels in one line. So this is the number of iterations. So how many times we have to do the copying. And screen size gives us the total amount of pixels. So if we had so iterations would normally be how many pixels we have to copy, and the screen size gives us the total number of pixels in the entire screen, and we have to copy that minus how many pixels are in one row. So we don't copy the row 0 to anything above. So we do the copy iterations amount of time, right? So what I'm doing here is, imagine there's a pixel around here, and I need to copy this to the one above, right? So I plus pixels per line would have given me this value, so this one, and then I copy that to this one. But since we're looking at 2 pixels at a row, we basically divide that by 2. So if I'm at pixel I, let me get rid of this. So this is I. Then I plus pixels divided by 2 would give me the pixel at this row. So that's the copy, and then we clear the last line. So screen size minus, so this is the last, so this gives us the index of the last line, and then we do it until the end of the line, end of the screen. And what do we set it as? We'll set it as according to the busy color. So let's look at it again. We do init, and init will use right star and right star, and right star will, if the linear cursor is above the textual dimensions of the screen, then we call print over the scroll. It will copy everything upwards. After this function is executed, we'll have an empty row at the bottom. So we subtract cursor by how many text fit in a single row, and then we calculate x and y positions, and then we call draw star. And yeah, this must be self-explanatory. If it is something other than printable character, then I just write what, the question mark. And new line, as for new line, I don't need to call scrolling until we actually need it. So a new line is basically the spaces until we reach the end of a line, and tab is spaces until we are at a tab width. Okay, and yeah, and I've also written a OS O1B library, and in my build.jig file, I create a module, and then I add it to the module of kernel. So I can in main, and I can just do import O1B, and OS will expose these various types within live. And I also created a CPU. I mean, I will get and some of these functions are because I'm also implementing interrupts, but so something like halt. Instead of using ASM, I just use the function, and it in turn calls the ASM volatile keywords, right? And is the panic function. It basically just does halt. And yeah, that's mostly it.